Where we're going is, so we're done with Maxwell-Boltzmann, and I know there's some equations across the board. The main thing about Maxwell-Boltzmann is it's an introduction to statistics, gets you thinking statistically because quantum mechanics is statistical. The part that will translate is the calculation of an average value. In quantum mechanics, you calculate observables the same way you do Maxwell-Boltzmann. Slight difference, but we're getting there. So that's why we do that. The other thing is that we're going to spend this week on a ramp up to quantum, and then next week we actually start quantum. We're going to do quantum the rest of the semester, except for a little bit of kinetics. I don't spend a lot of time on kinetics because it's like so many things. I know I've said this a zillion times. Enter the computer age, right? Now before computers, if ever you analyzed something, here's a population over time and it decays, your knowledge of kinetics had to be really quite good because nothing could do it for you. But now computers can, and it's ridiculous. So I do still cover it, but I do so at very minimal because this is like an old science at this point. Computers, this is one of the things like computers wiped out, like automation wiped out, some low-level welding jobs. Anyway, so we're going to spend the rest of the time on quantum. Quantum is, you solve the Schrodinger equation, right? Right? Does that sound right? Wrong. No, you do not do that. The Schrodinger equation, quantum is, I find it very dissatisfying. There is no straightforward way to approach a quantum mechanical problem. There's no algorithm. The Schrodinger equation is not a thing to be solved. It's actually more like a referee. It tells you what the solution must look like. It doesn't tell you how to solve it. And that's like very unsatisfying from my perspective. So what you can do is we will do this half the time, you often solve quantum mechanical problems without the Schrodinger equation. What you then do is check whether your answer is correct with the Schrodinger equation. If it satisfies the Schrodinger equation, your answer is correct, but you never use the Schrodinger equation to get to the answer. And again, that I find funky and weird, and that's exactly how it works, and we're going to see a little bit of that today. Okay, so we're getting there. That'll be next week. This week we're covering, today and Wednesday, we're going to do a very similar problem. We're going to do a problem that is very quantum mechanical in nature, but is not quantum mechanics. It's slightly easier. But it will get you thinking along those lines. So we got you thinking along the lines of probability. Quantum mechanics is fundamentally a probability-based mathematics. It's a mathematics of probability. Today we're going to start on wave mechanics, an introduction to wave mechanics. Again, it is a problem. We're going to solve a problem on light bulbs. We're going to figure out how light bulbs work. You run into a lot of quantum mechanical principles without some of the greater difficulties of quantum mechanics, but then we'll start on that next week. So that's the idea. Anyone have any questions before we go further? Right, so, oh, you're just waiting. Anyway, no questions though, no questions? Okay, so, all right, light bulbs. Again, we're going to run into a lot of the problems that you run into in quantum mechanics with the light bulb. So this is around, I think this is, oh God, actually I should know, this is like around 1900 to 1930. Mostly, a lot of science exploded at that point because they started having electricity in labs. And they started realizing that a lot of thermodynamics, which was mostly figured out before 1900, like literally 1880s to 1900, they started applying all that stuff we did last semester to light bulbs, and it doesn't work. It's like way off. Incrementally, they figure out things like photons. That's what light bulbs do, right? Photons are not particles with mass. You don't treat them like they have kinetic energy. You figure that out, and yet you still mess things up. Anyway, so that's what we're going to do. We're going to start coming up with models of light bulbs and derive equations with thermodynamic information that will lead to wrong answers, and eventually we get to the right one, and you start to see the wave and wave mechanics, and then we launch into quantum mechanics, and it will flow relatively straightforward from there. Okay, and also on the homework, if you haven't looked at it, you should have. I do have you looking at, here's an interesting thing. On the homework, I introduced Einstein's theory, Einstein's energy equation based on relativity. You guys have looked at that? Any of you? Right? It's a relative. So what do you do with that? You calculate the momentum of light, right? Wait, is that what I did? Look, I'm kind of not remembering. Isn't that what I did?
Yeah.
Right. Okay, so I know that in popular literature, and I'm going to debunk a lot of popular literature. The cat is alive and dead. Who's heard of that one? Okay, that's wrong. That is a bastardization of what quantum mechanics does, and it's largely unjustifiable. A lot of what you've heard is really wrong. When media describes scientific stuff, they get it wrong. So we're going to fix a lot of that. So what was actually I totally forgot where I was going with that. I am blanking. Yeah, quantum mechanics. You often hear quantum mechanics and Einstein relativity have, they clash, right? You've heard that before? The world of the small and the world of the big don't match. That's really not true. It turns out that that homework problem you're doing, where you use Einstein's equation of energy based on relativity, from that, Einstein figures out that photons have momentum. Now, the weird thing is photons have no mass. How can something with no mass have momentum? I don't think we still know. They do, though. Now, what happened is, and I'm preluding to next week, what happens is de Broglie says, okay, if light has momentum despite having no mass, then things with mass and momentum have wavelength. And that is where you get quantum mechanics. So anyway, so preluding on that. Again, the point is that a lot of what you hear in the literature, in the popular media, is really badly wrong. And one of them is that quantum mechanics and relativity don't mix. That's flat out wrong. They do have a fundamental disagreement, though, and that's on gravity. I actually will talk about Einstein stuff every now and then because it's kind of interesting, maybe a little bit more interesting than a light bulb. Gravity is where there's a major problem because, okay, two masses, right? What determines their force, their masses, and what?
Distance.
Distance, right. Okay, quantum mechanics says that you don't ever truly know where something is. If it's moving, you also don't know where it is. Now, how can you know the gravitational force between two objects when their locations are not precisely known? How can you do that? The answer is no one knows, right? That is the break between relativity and quantum mechanics that no one has really successfully figured out. So anyway, more on that some other time. It is kind of interesting how all this works. Okay, so in the homework, if you haven't done so, what you do is you use Einstein's relativity equation to show that light has momentum. Let me just remind you some things about light as it applies to this class, to almost everything that we do in science. You treat light as an electric field. And in physics class in E&M, you've learned about things like Maxwell's equations, Coulomb's law, all that stuff. I'm going to assume that you remember some of this stuff, although I still will cover it because I'm not going to leave you hanging like that. Even Maxwell's equation, we're going to do some Maxwell's equations today. I don't know that you remember them all, I don't know that I do. Okay, anyway, so light's an electric field, and equations of electric fields are not unknown. Okay, let me throw one new thing at you. So you're used to light being a wave and it's an electric field. Let me throw something that kind of makes a lot of this easier, and that is what we're going to call the K vector. That's the momentum vector. It's just the direction it's going in. Momentum, if you think about it, momentum is mass, which is a scalar that just means a number, times velocity. Velocity is a vector. Velocity tells you where you're going. So momentum is also a vector, and I can associate a vector with the direction of a photon, and I call it K. Quantum mechanics is completely centered around momentum. Everything in quantum mechanics comes down to calculating momentum. Heads up on that. So we're not going to have to worry about that right now, but understand by the end of class, you're going to be so sick of e to the I kx, where k is momentum. You saw that already, right, on the homework? Taking derivatives of e to the I kx, you're calculating the momentum of a photon, by the way, when you do that. Right? Neat. Okay. Now, a little bit aside from this, and I have no idea if I can do this right.
The magnetic field.
Yeah, magnetic fields. Right, and I'm trying to draw that.
Can't chew it out.
Well, yeah, like 90 degrees, and let's see, my ability to draw in 3 dimensions on the board is quite limited. So this, of course, is the B vector. And the magnetic vector, 90 degrees and, wait, is it out of phase? I'm drawing it out of phase. Actually, I don't know if it is out of phase. Oh, Jesus, I looked that up. Sorry about, no, I think it is out of phase. Anyway, it turns out that a photon is an electromagnetic wave, right? It has an electric field and a magnetic field. Magnetism is weak in this universe, and I can't help but drop Einstein stuff. Apparently there's 10 to the 400 universes. All of our universes differ by the nature of some of the, like the speed of light. In our universe, the speed of light is whatever it is. In another universe, it's different. In another universe, magnetic fields are stronger than electric fields. And anyway, so that's, you read Stephen Hawking, Einstein stuff, you run into that kind of thing. In our universe, magnetic fields are weak, and you can almost entirely ignore them. If you do very esoteric spectroscopy, something called circular dichroism is important. Of course, if you're doing NMR, like organic lab, then of course that's magnetic. For the most part, we can just ignore it. We start with electric fields, and if you become a spectroscopist, if you go to grad school, then you will also have to take into account magnetic fields. And anyway, so we always start, we'll start easy, right? So we'll start with just the electric field, and we're not going to worry about the magnetic field this entire class. All right, anyway. Now on the next homework, if you haven't looked at it, I also have some information about, more about photons, and I'll leave it for the homework and then maybe talk about it a little bit later, but anyway, that's coming up. Okay, now anyway, all right, so we're 1900. 1900, there's light bulbs, and of course people feel like they need to be clever and they need to describe the light bulb. What they want to do is describe the spectrum and the warmth that comes from the light. Not necessarily, we know that light bulbs are wasteful in terms of generating heat, but let's stand in front of the light bulb and let's think about the energy that hits us via photons coming out of it. So I want to know what the spectrum of the light bulb is, and I want to know how much energy is radiating out of it in the form of light. Let's not worry about inefficiencies. Like last semester, we didn't worry about inefficiencies. We won't worry about the fact that it's just kind of wasteful. So anyway, all right. Now we have to start out with one thing. We're going to assume that light is a wave, and they figured that out. Like, you see this old picture of Newton holding a prism, and light's diffracted. So they had a really good idea for a long time that light was a wave. And so we're going to start there, right? We're not going to start like in Stone Age times where we assume that light is like, a god of some kind. So if light is a wave, it has to fit inside of, okay, I know I'm trying to, what kind of light bulb is square? A square light bulb is something that's going to make this lesson a million times easier. Let's assume light bulbs are square because, oh God, if we don't, then you run into the same answer, but it takes 10 times longer. If you make the light bulb square, this analysis is a bazillion times easier, the light bulb square. Okay, now the reason that I want to use a square light bulb is that I need to figure out, so if light has a wavelength, and again, they knew that by 1900, they also figured out something astounding. The wave has to fit in the box. There you go, that's it. Okay, now let's say that the length is L. The length is L, so let me just draw that. I'll just draw a line and I'll say the length is L. And they figured out, now I have to admit, there's one thing that's always bothered me about this, and I never really understood this, is that, let me start drawing waves that fit. That's your first wave. Notice it's only a half wave. I swear I don't really get this. It seems like I would need a full wave. But a half wave technically counts. A half wave fits in the box. Now we can't do longer. What we need to do is have the wave or some multiple of the wave fit in the box anywhere in between. If it's a little bit longer, you know what I mean? It's a little bit longer. That photon is not in the box because it doesn't fit. That's the idea, right? It's actually kind of sensible. The idea being that, and I can actually tell you a little bit about this. here's the idea. And maybe don't write this down, I don't want to confuse you. Okay, so this fits in the box, right? That's what I just drew. But the idea is that this would not exist inside the box, it would just fly right out. That's kind of the idea. So anyway, so the light has to fit in the box.
What do you mean by fit in the box?
The light bulb box. Remember, we have a box type light bulb, because again, by the time at the end of this, you'll see that a box shaped light bulb is way easier to analyze than a round one. Trust me, you get the same answer. So now the reason is that, well, you'll see. So just trust me, the light bulb is a square. Right. So anyway, okay, what's the wavelength? What's the wavelength? Now you see, it's a half wave fits the entire L. 2L, that's right. Right, because remember, the L is half the wave, right? Or the wavelength is 2L. You know, dot, 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 and I do a full wave. Let me just do a full wave. That'll make it a little bit easier. Okay, now again, the length is L, so just assume that this fits in the box. That's legit. Now again, if it was a little bit stretched, and the end was a little bit outside, it really wouldn't exist inside the light bulb, it just wouldn't. So the wavelength is what? This should be very easy. It's just L, right? Okay, now let me do this. Let me write it this way. You'll see why in a second. It's L. I just wrote the wavelength is L. Of course it is, right? This is in high school. I wrote it kind of funny, but you'll see why in a second. Okay, the next wave that fits in a box is actually this one. Hopefully I won't screw this up. Did a little bit. Again, hopefully you see now, if you were a little confused what I mean by fits in the box, these fit in the box, so hopefully the pattern is obvious. What is the wavelength? What is it?
3 over 2.
3 over 2L. 2 over 3, right? 2 over 3, it's just geometry. Now, it's very easy to get that. I get those flipped too. The way I remember this is that the wavelength is getting shorter and shorter. That's the way to try to keep that straight. Whoever said 3 over 2, I also will do that quite frequently when I'm writing these out. But again, the wavelength gets shorter and shorter and shorter. Okay, now here's a hint, and here's something you want to notice. This is going to lead to a problem. The wavelengths only get shorter. It looks like 2L, let's parameterize it by an n, and we'll call this n equals 1, n equals 2, n equals 3. And the thing is that goes on forever. There's a limit on how long the wavelength can be, but there's no limit on how short the wavelength can be. And this will lead at the end of next class, that leads to a crazy problem. Just foreshadowing, because I told me to do that, you're going to burn my house down. I can always fit shorter waves in this light bulb box, but there's a limit on long ones. Okay, again, this is going to lead to a problem that stymied people for nearly 10 years, and they basically figured out quantum mechanics as a result. Okay, light bulb light wavelengths, right? High school level physics, high school level E&M, no problem. Next step. Okay, if light is an electric field, Maxwell's equation, I don't know how much flack you get on this. Maxwell just amalgamated a bunch of other people's equations and gave it his name, which, cool. One of them, this is a derivative of the Maxwell's equation, the Ampere's corollary, anyway. This describes an electric field. So just remember, I drew an electric field. Let me forget the little hats, the vectors, because it just sucks, because I'll forget half the time anyway. Okay, so in one dimension, the change in the derivative of an electric field, these things change over time. So it's a double derivative. So the double derivative of an electric field in space is equal to the same over time. You've got to make sure the constants got to work out, right? So this is one electric field over meter squared. So this is electric field over second squared, so you need some kind of fundamental constant to make sure the units work. So you have some translation factors here, so that's what that does. Okay. All right, now let's not forget, I'll do one more thing and then I'm gonna leave it up to you to figure out what the heck I'm supposed to be doing. One dimension, all right? What's the problem?
They're not the same.
How many, now, when we did Maxwell Boltzmann, what did I keep saying over and over again? We lived in how many dimensions? Three, okay, so I warned you several times last semester in this one, and you've already seen it. How many times am I gonna write equations across the board? Answer every day. This is going to get nightmarish, by the way. This one's pretty bad, and that's why it's actually relatively easy. It's just that, notice that this already looks kind of nasty, and the reason is that I'm writing the same thing a bunch of times. That makes it big and large and oh no, but reality is each one of these really looks basically the same. Okay, regardless, all right, there we go. Okay, so this is the Maxwell equation deal. This is how E and M works. Space, unfortunately, time happens, so we have to include that. And I know photons are an electric field, and I know that they have to fit in the box. My question to you is, what do I do next? I mean, what am I even setting up? I have this equation here. I've got a light bulb and I've got some waves. What am I even trying to do? It doesn't help that I haven't told you, but I want to see if you can kind of figure it out. Okay, let me okay, if those are the electric fields. Could I give them an equation?
Relating the wavelength to the energy.
Yes, we can relate wavelength to energy. But before, and what I didn't want to do is relate that to the energy coming out of the light bulb. I did hint that at the beginning. Remember, I want to get the spectrum and the energy coming out of the light bulb, but we're doing baby steps. This is the first baby step. Again, do you think you could mathematically describe what I've drawn up here?
Yes.
With what? What kind of functions? Sines and cosines, sure. Well, I think we're going to go with sines. We could do cosines too. Sine function, all right. Okay, so what? So I look at that and I can do a sine function. How do you know whether that's okay or not? I mean, I know I drew some waves. Nothing says that that's correct. How can I know whether that's correct?
Plug it into that function.
What was that? Oh, plug it into this function. Right. Okay, so first taste of quantum mechanics. Wave equations better fit the referee equation. This is like the overlord. If it doesn't, then you're wrong. So that's the idea. So can I mathematically describe electric fields? They better fit Maxwell's equations. These are electric fields, and we know that this works. Okay, awesome, right? Now, here's the thing. Let's do that for the hell of it, but what we're going to get out of it, what magically pops out, we're just doing this right now for the hell of it. I think those are sine functions, but if I'm right, then it'll fit in this. But when you do that, other stuff starts to appear. Not that you're necessarily going to go for that, but it does pop out. What pops out, by the way, is the energy of the light bulb. That's where we're getting to. All right, now, as I warned you a gazillion times, I am going to write something across the board. It is hideous, but let me before I begin there, I need to come up with an equation for the electric field. See, I know you can write sine of x up there. Looks like I need to include some here. Let's write some constant that tells you how strong the electric field. I'm sure it's like 1 over 4 pi epsilon naught. You remember that? That's the permeativity of free space from classical EM. Anyway, you don't need to remember that stuff. Let's give it a certain oomph. Let's give it the electric field with strength. I'll just call that. Whatever, we're done. Okay, now I'm going to have, let's do the x. Okay, so we decided a sine function. Now, Okay, x, you better have an x. But I have to have other stuff inside of it, or that doesn't happen. Right? I need to have a frequency. And I can't have any frequency, right? Or wavelength. 1 over frequency is wavelength. How do I do that? Here's a hint. When x goes as far as L, let's look at the first one. When the wave has traveled to L, sine needs to be fed what? Right, now what is the value? Let's look at the first wave. We'll worry about the others later. When we've traveled L far, when x is equal to L, sine, the wave is equal to what? 0. And what do you feed sine to make a 0?
Zero.
No, pi. Actually, I know, I have to Google that stuff.
The integer multiple of time.
Right, an integer multiple of pi. Okay. So again, when x has gone to L, because I actually don't quite remember. Yeah, you got to get a pi. So pi x over L, right? So that makes sense. When x has gone to L, you've got to go from 0 to pi. Totally works. That is the fit of that function, but what about the others? Okay. Now, how would I describe the second one? All right, if x has gone to L, then sine needs a 2 pi. How would I do that? What could I put in here to make this pi a 2? And the answer is shockingly simple. 2. Okay, but now what about the next guy? How would I make 3? Actually, I'm a little bit flummoxed myself. Anyway, what the answer is plug in n. If n is 3, I think that works. 3 pi. Right, 3 pi. It goes 1 cycle plus a half, right? So you see what I've done? So depending on what wave you're describing, whether the n equals 1, let me label that with a lowercase x. I'll write that bigger for the video's sake. Okay, there you go. All right, so if I'm describing the lowest energy wave, the longest wavelength, this is 1, and hey, there you go. N equals 2, I get that second one. N equals 3, I get the third one, and on and on and on. Right? You're okay with that? Again, it's just a model, but it reproduces what I've drawn up there, including all the others. Question?
Should that be E sub x then for the energy in the x direction?
No, that's not energy. For one, that's electric field. So be careful about that. I haven't solved energy. Only so many letters, right? I know E is also energy, but this is electric field. Okay, now to answer that question, I can't stop with x because I have to include y and z, right? Now here's where you have to then use your hint. It's just like the Schrodinger equation. You have to look at this, and this thing dictates, it doesn't help you solve the equation, but it tells you what the solution looks like. And again, this is funky, but you have to get used to this. Okay. Now, I need to include x. I got x. I got that down, but how do I include y and z? Now, of course, the waves in y and z are identical, but how do I include them? I could do this. Now, here's an aside. I could do things like this. Now, constants and blah, blah, blah. I could do this. I could do this. Now, again, constants, I'm just saying. I can really think of just 3 ways to do this. I could simply say that there's a sign of an x and a y and a z. I can add them together. I could multiply them. Okay, anyone wants to vote? 1, 2, or 3?
2.
Okay, there's a variety of answers. Now here's the thing. This thing has a clear winner. Now your math skills, if you were math majors in your senior year, you would know instantly which one it is. So, but you're not math majors, so I have to tell you, and let me logically explain what's happening. It turns out this is the winner. That is the right one. And you're actually going to do a homework problem where that's going to be more evident, but that's a ways from now. Now, the reason that this is the winner is because of this. It turns out that, this is unfortunately kind of hard to explain. I'm going to do my best, obviously. What happens is, this describes how the wave is changing in x, in y, and z. And they're all equal to something that is not changing in x or y or z. So that implies that there's two ways to think about this. This implies that they all affect each other, right? So if this guy gets out of hand, so let's just say this guy's going to do what it's going to do. If this guy gets big, then this guy has to get small in response. See what I mean? If this is just what it is, that means that this thing is changing a lot, and this thing has to respond by changing less. Because and vice versa. If this decides to change less, then this has to get big because it can't, it has to equal this thing, which doesn't care. Maybe, and let me try to draw that. Let's say that we have a particle and we shoot it in the x direction. And you have a function for its position. You have a function for its position. Now imagine that I shot it catty corner. There's a y direction. Let's say I shot it catty corner. I would shoot it faster, square root of 2 faster, so that there is a y position. Okay, there's a y position. My question to you is this. How does this function depend on y? It doesn't, right? So when I shoot this in this direction, its velocity, it'd be like velocity times time. Now, if I angle it, and I give it a little bit more oomph, it can have the same equation, right? I mean, it can move just as fast along the x director as it was whether I shoot it along x or catty corner with a little bit more oomph, right? You accept that this would be the same equation, right? Right?
Yes.
Yeah? So, that means that they're independent of each other. So that means that you can't state that if this guy decides to change less, that this will then respond by changing more. It can't do that. So again, it's just an example. The solution to this is that each term is a constant. And this term's a constant, that term's a constant, and that term's a constant. Every term is a constant. And what that does is it makes it work. If a plus b plus c equals d, then a plus b plus c is equal to d. And a plus c, it never changes. If you get the right equation, you're going to get a series of constants. And of course, 1 plus 2 plus 3 is always equal to 6. Anyway, yes. Okay, now in terms of what I just described, each term being a constant, this makes that happen. And again, you're going to do a homework to show that. So it turns out that this is the right solution. So therefore, oh crap, now a major problem of this class is the fact that I run out of room because these equations are so freaking long. Okay, sine, and again, the other directions are identical. They just got y's and z's. And these, now I'm going to call these, I have a name for these n's, I'm going to call them mode numbers. Just to, doesn't really mean anything. But, well actually, mode would refer to the number of nodes, right? So a mode number of 1 has no nodes. Look at the top. So top 1, no nodes. N equals 2 means 1 node, N equals 3 means 2 nodes. There's your node in case, I forgot. These don't count. So 2 nodes, 1 node, no nodes. So I use the word mode number, and again, that doesn't mean a lot. It tells you the number of nodes. It also then tells you the frequency, 10, so that's coming up. All right, now what? Okay, now what you can do is take this and plug it into here. Oh, this is gonna suck. Yes, I'm going to do that, and I'm gonna see what the heck happens. And what happens is horrible. Well, it's not horrible, it's really, again, I mentioned this to you a couple times. I've been to grad school, I went to Berkeley, I was a postdoc at MIT, and I've only once ran into a mathematical something that I really was like, I have no idea, and I had to go to a mathematician to help me solve it. Every other hideous quantum mechanical something I've ever run into ended up being nothing but a bunch of constants multiplied, which really just wasn't that bad. Okay, so now I'm also going to have to write this out with a little bit of shorthand because it's just, it is a bit daunting otherwise. Okay, now here's the thing. So I'm going to plug this into that equation into this. And again, I'm going to have to use a little shorthand. Okay, so what have I got? I've got the double derivative of sine. I've got the double derivative of sine, and you've already done some homework, so what I'm going to pick up is, I'm going to pick up the constant and that n sub x squared and pi squared over L squared. Now again, that's the double derivative of sine, just like your homework. Okay. Now, of course, the equation didn't disappear because that would be weird. And x pi x over L. Okay, now shorthand, folks, shorthand. Oh, wait, I've already written that for x. And I also have to have a function of time. A function for time. Did I, I'll write that down in a second. You actually do the next homework assignment, which is already posted, by the way. Don't turn that in tomorrow, right? Start on that's Wednesday. So I have to have a function of x, y, and z and time. I'll show you the function of time here in a second. Sorry, I should have done that already. Tell you what, here it is. I'm a little shorter. This kind of makes my head fall apart sometimes. It's assuming the E naught is there, what it is sine. It's all very sensible. I wish I could tell you a little bit more, but it's on a homework. And again, if you think of the speed of light as meters per second, time is in per second, you end up with 2 pi over lambda. Anyway, if you think of, let's say that c over lambda is the frequency, what you end up with is 2 pi times the frequency times time, which is the equation of a wave varying in time. So that's my just answer one of the questions. Anyway, okay. Now f of y, of course, is sine ny pi y over L. F of z is sine nz pi z over L. I don't want to write it out because I've only done one term. Let me do the next one. Minus E naught and y squared, I squared, L squared, sine. I got to remember that this is the y guy. I'm going to do one time. Okay, of course, the x is still there, the z is still there, the t is still there. Next one, so you see, this one is so bad, I can't even write across. I can't even do that. And it'll be a miracle if I don't slip. I forget? Okay, then I've got x, I've got y, I've written z, so I've got time. And then I've got to set that equal to the derivative with respect to time. So I've got, I've still got E naught. Let's see, do I pick up a minus sign? Yeah, I've got minus E naught. Okay, again, the strength of the wave. The double derivative is going to draw out a c squared, 1 over c squared, a 4 pi squared, 2 pi squared. No, sorry. That c squared is right here. Then I'm going to multiply by c squared and over lambda squared. Okay. 4 pi squared c squared lambda squared. Okay, there we go. Okay, it's fine. The function is still there. 2 pi c t over lambda. Then I've got f of x f of y, f of z. There you go. Okay, so again, that's my equation, and I'm sorry, I should have included this term in there, so I screwed that up, sorry about that. I've applied that to this SOB right here, and here's the result. And it looks hideous. Okay, and it is, I mean, look how big it is, but that is all it is. It's just big. It's a bunch of sines, a bunch of pi's, a bunch of l's. That's all it really is. Now, because that's all it is, I can simplify it. Oh, sorry, I'm smarting about that now. Let's see if I can maybe put that in the video. I'll fix that in a second. Okay. All right, now these are equal, but now here's the first trick. All these f's of x, f of y, f of z, f of t's, they all factor. And they factor in this way. So this is a simplification. I'm working the derivation, I'm just going down. So I've got E naught pi squared over L squared comes out every time on the left side, and x squared. You see, the only thing that varies when all the top three terms is just the mode number squared. Other than that, it's all the same. Then you got f of x, f of y, those again are the signs, equal to E naught, I got rid of the minus signs, by the way, 4 pi squared, c squared over lambda squared, f of x, f of y, f of z, f of t. Sorry about that. You see how hard it is to like plan ahead when these things are this long? Question?
Shouldn't the C cancel or no?
The C's cancel, but let me see here. Yes, they should cancel. Yes, right here. You're right. My notes are wrong.
The pi squared on the left-hand side?
Well, yes. Now let me not go too nutso with the pi squared on the left side. Yes, that should be right. Right. Thank you for pointing that out. Okay. Let me not do any more cancellation. Let me just go one more step. I don't want to do too much at once. Okay. Well, let me just point out right. So we're going to wipe out the pi squared. The main thing that gets wiped out real quick are you saw what I did? You see what I did? It's like this is the mistake I'm making today. I'm forgetting the T. I just keep forgetting it. There we go. Okay, these cancel out. Okay, now remember what I was saying, how these, you have to write the electric field as x times y times z, f of x times f of y times f of z. You have to do that because when you do these double derivatives, all of the functions actually cancel out. You see, it ends up being a bunch of constants. Remember I said that the derivatives are actually constants. You're seeing that now. Here, let me simplify that. Let's get rid of the E naughts. Let's take care of the pi's. And we got rid of all the sines and cosines. And what we're left with is an x squared plus n y squared plus n z squared equal to the remainder of the constants, or 4L squared over lambda squared. There you go.
Professor, does he have an ft on the last equation on the left side?
YZ.
What's that one?
Yeah, because they have it on the left and the right side of the top equation on there.
Wait. So I have 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Wait, what am I missing? I don't see.
We have t.
The T is here.
F of t, is it supposed to be f of t?
It's right here.
Oh, you just showed it. Yeah.
Well, yeah, no. So when I did the x, double derivative of x, I wrote out the function so that you're not lost, right? This is sine pi n sub y over L, n z over L, right? So I'm just not writing the signs out every time because it would kill me. You see, x, y, z, f, x, y, z, t. sorry, X, Y, Z, T, X, Y, X, Y, Z, T, X, Y, Z, T, X, Y, Z, T. They're all there, right? Okay, so what that ends up with is this. And now what you see, what you get is, remember what these guys do? These are related to the number of nodes, which is going to be related to the wavelength or frequency. Wavelength or frequency. From the wavelength I can get the frequency, right? C over lambda is the frequency of light. What can you get from the frequency of light? What can you get from the frequency of light? Right. Okay, you see what you've done? You now know the energy. This is actually, I mean, this is number of nodes, but it's really wavelength. Wavelength is frequency, frequency is energy. This is the energy. And it's a function of the length of the size of the light bulb. Okay, so what so frequency is here, but there's one more thing you need to know. It turns out that there are, let's take the lowest energy wave, which I erased. Let's take this lowest energy half wave. It turns out there's three of them. There's one in X, there's one in Y, one in Y, and one in Z. There's three of them. What about with a single node? How many of those are there? Turns out there's also three. 1, 2, and 3. Okay, as you go higher and higher, it turns out there's more waves will have the same number of nodes, which have the same energy. So here's what you're going to do. You're going to count up the number of waves times their energy. And that is the energy of the light bulb. So that's where we're going. This gives you the energy of a wave times the number of waves is the energy. We're going to add them up, and that's the energy of a light bulb, and then we're in the next week. All right, everyone.